Welcome to this Tech AV training program, which has been produced in association with John Crane Pty Limited, manufacturers of high-quality mechanical seals and gland packings. In this program, you are going to learn the basic principles of an important industrial topic, namely that of mechanical seals. During this program, you will learn to describe the fundamental principles of mechanical seals, identify the different types and designs, and learn some important facts about mechanical seals that will assist your maintenance and diagnostic skills. The advent of mechanical seals began way back in the 1940s, when many industries began pressing manufacturers of shaft seals and packings to develop leak-free devices on their centrifugal pumps, agitators, mixers, and similar equipment. But let's first go back a moment to packings. As you recall, packings are dependent on a flow of product or liquid at the interface of the shaft or sleeve. When wear occurs, the leakage past the packings increases. And if the packings are even slightly overcompressed, then the liquid barrier can be destroyed, resulting in overheating and shaft or sleeve damage. This means constant attention and increased chance of error. Early attempts at producing maintenance and leak-free seals began with engineers designing an end-face type seal that relied upon a shaft shoulder running up against a machined housing. The design was by no means perfect, as no allowance was made for shaft end play or axial float, which meant that the seal was broken and leakage occurred each time the shaft happened to float back. Further, no allowance was provided for any shaft whip or runout, which inevitably occurs. This too prevented effective end-face sealing. Clearly, what was needed was a seal that was able to float both axially and radially, but still maintain parallel face-to-face contact at the sealing surfaces. In other words, the seal had to be flexible. The devices subsequently developed, and which are extremely effective in achieving the desired leak-free effects, are today known as mechanical seals. In principle, a mechanical seal comprises a primary seal of two flat polished rings that rub against one another. One ring is kept fixed or stationary, whilst the other rotates, usually driven by the shaft. Face-to-face contact between the primary seal face and the seat is maintained with a spring, or a series of springs. For purposes of further explanation, let's imagine the seal to be cut in half. In this way, we see a section of a seal which would look like this. In order to provide a seat or base for the springs, a shoulder is necessary. This could be a stepped portion of the shaft, but more commonly it is a ring secured to the shaft. And this, as we'll see later, can also provide the means of driving the primary seal. Now, having created a basic seal, we still have areas known as leak paths that require extra sealing. Such an area is created between the shaft and the primary seal bore. To prevent leakage in this area, we need to create what is called a secondary seal. Three seal types are commonly encountered, namely O-ring seals, wedge seals, and bellows seals. It is common practice to describe a mechanical seal by its secondary sealing device. There are two main seal classifications, namely pusher type, that is where the secondary seal is activated by spring or hydraulic pressure, and non-pusher type, where the secondary seal is fixed to the shaft. However, let's overview the principles of a typical secondary seal, such as the O-ring type. Here, an O-ring is situated into an annular groove, usually cut into the primary seal. As hydraulic pressure occurs behind the O-ring, the rubber is forced to deform into the leak path, thus effecting a seal. When the pressure is released, the O-ring will revert back to its original shape. However, there is always some amount of axial and lateral shaft movement in any equipment. This results in the eventual wearing of the O-ring. shaft fretting, and subsequent leakage after a period of time. O-ring seals are still popularly used, mainly due to low cost. They are suitable for low to medium temperature operation and in mild chemical conditions. Let's look now at the wedge seal design, which utilizes a wedge to create the secondary sealing effect. In this design, spring pressure plus a small amount of hydraulic pressure forces a plastic wedge, usually made from Teflon, into a bore at the back of the primary seal. Point loading spreads the wedge to form an effective seal. Bellows type seals utilize a simpler secondary sealing method. In such a seal, the actual secondary sealing point is effected by fixing rubber or elastomer bellows to the shaft. The other end of the bellows is fixed behind the primary seal. As axial or lateral movement occurs, the bellows flex or extend. Because secondary sealing is not dependent upon spring or hydraulic pressure, we refer to this type of arrangement as non-pusher type. Returning to the leak paths, we have one area of concern requiring further sealing. That is the area between the stationary seal component and the housing. Sealing at this area is called tertiary sealing. Methods of tertiary sealing include the use of an O-ring situated into a groove within the seat or into the housing. More commonly, an O-ring is situated into a recess. Another popular tertiary seal is the cup seat, whereby the stationary ring is supported and encased by a rubber cup. Of earlier design, but still in use, is the clamped seat seal. In this type, a gasket provides the tertiary seal and the cover plate serves as the primary seal seating. After the break, we shall discuss various drive methods for mechanical seals.